So, good morning everyone. This is the 7th lecture in this sequence and we will start a new chapter today. This chapter is going to be slightly theoretical in nature. There will be very few problems, but it is essential. I mean, this is a minimum theory that should be done in a course for college teachers. Of course, even some of these proofs could still be cut down when you teach your students, but at least as a teacher you should know the proofs of these theorems, and this is the bare minimum. I mean, we should be doing much more than this, but given the limited amount of time, this is all that we can do. Alright, so the title of the chapter, this is chapter 6, the title of the chapter is Further Consequences of Analyticity. Under this chapter you will see several items, but each one is a small item. Power series representation, that is a theorem that an analytic function is locally representable as a power series. The second item is a Cauchy's estimates and Liouville's theorem. The third item is zeros of analytical functions. We will prove that the zeros of an analytic function are isolated. Then the next thing is Riemann's theorem on removable singularities. It is an important theorem, it is an easy theorem, but very important. And then the one thing that is optional, but I still decided to put it here, is the maximum modulus theorem and the classification of isolated singularities and poles and residues. The last topic will be required for the next chapter. Okay, so maybe if you do not understand the maximum modulus theorem, you can still understand the next chapter, but if you do not understand what is a pole and what is a residue, you cannot understand the next two lectures. Okay, so please pay attention to what is written in blue. Okay, so let us get to business right away, and I already told you what the theorems, some of the theorems are. So the theorem is on power series representation. The first theorem is on power series representation as a topic, as a list of subtitles indicated in the previous slide. So what does the theorem say? Suppose omega is an open set and f is a function from omega to c which is analytic. Then, so here is a picture of omega and you have taken a point A in omega, then there exists an r greater than 0 such that on this disk of radius r centered at A, the function fz can be expanded into a power series which is valid in the disk mod z minus a less than r. In this disk, this power series representation is valid, and moreover this tells you how large can this radius of this disk be. This is an important information. This is not some optional coda to the statement of the theorem. Please pay attention to this statement. In fact, r is the radius of the largest disk that can be inscribed in omega. So for example, if your domain is a rectangle, a thin rectangle, and you take a point in that rectangle, then you can have a small, then the disk in which the power series representation is going to be valid is not going to be this big, it is going to be this small. You can imagine a thin rectangle, let us say 5 units wide and 1 unit high. You may take a point right at the center point. So the radius of that disk is simply half, 1 unit thick, so half above and half below. It is not going to be valid, and so that disk can be inscribed in that rectangle. The power series will not in general be valid outside that disk, in general. Alright. There will be some restrictions on the domain of validity, but it will be valid at least this much is true, that you take the largest possible disk that will fit into your domain with A as center, then that radius is the radius on which in that disk the power series representation will be valid. Alright. There is a little more to the theorem. What are these coefficients a0, a1, etc.? Suppose I put z equal to a. Suppose I put z equal to a, all these things disappear and a naught is simply f of a. You differentiate both sides. Remember that the power series can be differentiated term by term, right? So differentiate both sides and then put z equal to a, the constant term that disappears. So you're going to get a1, but all these are going to contain z minus a, right? There's going to be a z minus a remaining after you differentiate, and then when you put z equal to a, those things will disappear. And so what is your a1? F prime of a, and so it goes. You can actually write down a formula for the various coefficients. So on the one hand, the formula is just the kth derivative, right? The formula for ak is what? K factorial ak is the kth derivative of f. Is that correct? All right. On the other hand, the theorem also tells you that the ak is also given by 1 over 2 pi I integral f zeta d zeta upon zeta minus a to the power k plus 1 mod zeta minus a equal to delta, where delta can be chosen to be anything between 0 and r. It is not going to make any difference what is the value of the delta, because if you take two different circles, then I can apply the Cauchy's theorem to the region in between. So the integral over the smaller circle will be equal to the integral over the larger circle. So the value of delta doesn't matter, you could take any delta between 0 and r. Is that correct? So now what am I going to do next? I am going to equate this representation of ak with the other definition in terms of derivatives and compare the two results. That will be done later. After we finish the theorem, the corollary will give you the two different expressions for ak, which will be equated, and we will look at the things. Okay. Before I begin the proof, yeah, please settle down, because this proof is important. All right. So first, choose any r prime less than r. First, choose any r prime less than r, where r is the radius of the largest disk that can be inscribed in omega. The r has not been properly specified in the theorem itself. Then fz is analytic within and on the circle mod zeta minus a equal to r prime, correct? You have the largest disk that can be inscribed in the domain, and now I am taking a circle which is concentric to mod zeta minus a equal to r, a smaller circle. Surely the function is analytic within and on this circle, right? So I can apply the Cauchy formula to this closed curve. Cauchy formula to the closed curve will give you what? It will give you f of z equal to 1 over 2 pi I integral mod zeta minus a equal to r prime f of zeta d zeta upon zeta minus z. Remember that the circles, the contours are traced counterclockwise unless otherwise specified. So that has not been specified anywhere, but it's understood. That's a blanket assumption. Now what I do is there's one trick and only one trick in this theorem to write this zeta minus z as zeta minus a minus z minus a and pull out the zeta minus a common and write this expression as 1 minus z minus a by zeta minus a. That is the only trick that is involved in this proof. Once you start with the Cauchy formula, this is the only thing you have to do, and the rest of the proof simply writes itself out very naturally. What is the next obvious step? Apply the geometric series, write this 1 over 1 minus this complex number as a geometric series. Why is it that I can write it as a geometric series? Because where is your z? Z is inside this circle, correct? So mod z minus a is going to be strictly less than mod zeta minus a. So the ratio is going to be less than 1 in absolute value. So the expansion as a geometric series is meaningful and is valid. Alright, so you do that, what are you going to get? You are going to get f of z equal to 1 over 2 pi I integral, the integral is the same, f of zeta d zeta is the same, I just wrote the geometric series. Remember that there was an extra zeta minus a over here. That is why you see a zeta minus a to the power k plus 1 and a z minus a to the power k. Now, as far as integration is concerned, z is an a are constant because I am integrating with respect to zeta. So, I can pull this out and I am going to interchange the summation and integral. So, I am going to get in summation k from 0 to infinity z minus a to the power k into 1 over 2 pi I integral f zeta d zeta by zeta minus a to the power k plus 1 mod zeta minus a equal to r prime, correct. Is it clear? That is a power series. Power series and the coefficient ak is nothing but this, right, and that is what you saw in the previous slide, right. In the statement of the theorem, I have put this ak was given by 1 over 2 pi I f zeta d zeta upon zeta minus a to the power k plus 1 over any circle that you choose between of radius between 0 and r, and I also explained to you that the value of the delta does not matter. So, these constants, so these coefficients are here. The last part of the theorem is simply to be read off from the proof. Is it clear? And a small comment, as usual when you exchange an infinite series and an integral, a word of caution is important. Somebody is going to ask you, the clever student in your class is going to ask you, how do you justify this step? And you should be in a position to say a few words to him, otherwise you will fall flat on your face. The exchange of integration and summation can be justified easily because the series converges uniformly with respect to zeta. Remember, how do you check uniform convergence of this? How do I check the uniform convergence? I am going to apply Weierstrass's M test, correct. In other words, I am going to take the kth term in the series, take the absolute value of the kth term and estimate. Now, in the kth term of the series involves a zeta minus a, and where is the zeta varying? Over the circle. And so, what is zeta minus a? It is fixed, it is a radius r prime. The f zeta is varying over the circle, so it will have some supremum over there, so put the supremum over there, m upon r prime to the power k plus 1, and then what is left over? Mod zeta mod z minus a to the power k. So, the supremum of the kth term with respect to zeta, the supremum of the kth term with respect to zeta is what? Mod z minus a to the power k upon r prime to the power k plus 1 into some m. M will be coming from the supremum of the mod of the function. So what is this supremum? It is a geometric series. Mod z minus a to the power k upon r to the power k plus 1. The geometric series with common ratio less than 1 converges. So, by Weierstrass's M test, the uniform convergence can be justified, and so the summation and integral can be exchanged. Right. So, you may not want to spell this out in your regular class, but there will be a query coming to you from somebody, and I think it is your duty to be clear about this. All right. So, that completes the proof of the theorem. So, once again, the function f of z has been written as an infinite series sigma a k z minus a to the power k, and the a k is given by this expression. And since r prime less than an r was arbitrary, the validity of this result holds on the disk mod z minus a less than r, because the r prime was arbitrary. The corollary is that the kth derivative of f at a equal to k factorial upon 2 pi I integral f zeta upon zeta minus a to the power k plus 1 over the circle. Why is that? You differentiate this power series k times and put z equal to a. You will immediately get k factorial a k equal to Fk of A, but the Ak is given to you over here. So, this formula falls out of it, right. This is a very important formula. So, you see how do you, okay, now how do you remember this formula? How do I know, oh my god, I am going to forget the k factorial? It is very easy. Do you remember the Cauchy formula? What is the Cauchy formula? F of A equal to 1 over 2 pi I integral f zeta upon zeta minus A. Now that is going to be true regardless of where the A is, right, as long as A is inside the circle. So look at this equation, f of A equal to integral 1 over 2 pi I integral f zeta d zeta upon zeta minus A. Differentiate both sides with respect to A. F prime of A equal to 1 over 2 pi I integral f zeta upon zeta minus A the whole square. The minus 1 and the minus 1 will cancel out. Differentiate it again. You will get f triple prime of A equal to 2 upon 2 pi I integral f zeta d zeta upon zeta minus A cube, etc. So once you write down the Cauchy formula, the formula for the derivative can be written down by formal differentiation with respect to A. Differentiating under the integral sign, right? Clear? How to remember this formula? Easy formula to remember. So the proof I had just spelled out. I had told you exactly what the proof is. In fact, f of z is this. Differentiate the power series k times and put z equal to A. You will get on the left hand side you will get Fk of A, on the right hand side you will get k factorial Ak, but Ak is given to be this. Compare that, put everything together and you get your formula for the derivatives, alright. Okay. Now let us come to what is called as a Cauchy's estimate. So now Cauchy's estimate says if you take the modulus of the kth derivative at the center, that is going to be less than or equal to k factorial upon r prime to the power k into supremum of f zeta over the circle. Now it is very clear where this formula is coming from. It is very obvious rather where this formula is coming from. You start with a formula. What formula you begin? You begin with this formula and take absolute values. And then the I will go away, you will get k factorial upon 2 pi, alright, and then the absolute value will come on this. Now how do I deal with the absolute value on this? Parameterize the circle and put the things. No, put zeta equal to A plus r prime e to the power it dt. Integral will go from 0 to 2 pi. What is d zeta? R prime I e to the power it dt. Mod I is 1, mod e to the power it is 1, r prime is a positive real number. So d zeta is giving you no problems, only the dt will come. What is the denominator? What is the modulus of the denominator? Look at the modulus of the denominator. Or rather first zeta will be what? A plus r prime e to the power it. So what is zeta minus A? R prime e to the power it. So it is going to be r prime to the power k plus 1 e to the power it to the power k plus 1. The next step I am going to take the modulus inside the integral and that e to the power it terms will all go. I will simply be left with r prime to the power k plus 1. Is it clear? That is exactly what I am saying here. So take the formula, put the modulus, the k factorial upon 2 pi, I goes away, you have modulus, you have integral of zeta minus A equal to r prime, f zeta d zeta upon zeta minus A to the power k plus 1. Now do the actual parameterization, put zeta equal to A plus r prime e to the power I theta, 0 less than or equal to theta less than or equal to 2 pi. The integral goes from 0 to 2 pi, absolute value has been taken inside the integral sign, and then you are getting f of zeta has some supremum, that supremum has been put over here, d zeta is I e to the power I theta r prime d theta. So that absolute value comes over there. Zeta minus a is r prime e to the power I theta to the mod to the power k plus 1. What are the only survivors will be the r prime and the m, correct? That is a constant, all of them is a constant, and so you are left with integral 0 to 2 pi d theta, that is a 2 pi, the 2 pi and the 2 pi cancels out, and you are left with f prime of a modulus, f, the kth derivative of f at a modulus is less than or equal to k factorial m upon r prime to the power k. This is a very important estimate, although the proof is very simple, proof is extremely simple, but the result is extremely important. Why is the result so important? The result is telling you that suppose what are you doing? You have taken a function f, correct, which is defined in some domain, and you are concentrating your attention on some disk, which is first of all you are taking a circle which is lying entirely in the domain, and you are taking mod zeta minus a less than r prime, and r prime is less than r, so that the circle is actually lying in the domain in question. So the closed disk is actually sitting inside the domain. So what are the things that are involved here? There is a m which is sitting here, and what is the m? It is the supremum of the modulus of the function. Derivatives are not appearing. Supremum of the modulus of the function on the circle, correct, that is your m. The other two things are what? There is a factorial present in the numerator, and there is a geometric sequence, right, r prime to the power k. So what is, and so your r is fixed, you think of the r prime is fixed, okay, think of the r prime as fixed, which means that your m gets fixed, right. So the derivative, the kth derivative grows like constant times k factorial times a constant to the power k. 1 over r prime is a constant, 1 over r prime is a constant, its kth power appears. A geometric sequence times a factorial, that is the bound on the kth derivative. In other words, the derivative, the sequence of derivatives evaluated at a point cannot grow too rapidly. You cannot have an analytic function whose derivatives at the origin are nth derivative of the origin is n factorial squared, where n equal to 0, 1, 2, 3, etc. In other words, I cannot prescribe, I can't tell you construct for me an analytic function whose derivatives at the origin are 2 to the power 2, 2 to the power 2 to the power 2, 2 to the power 2 to the power 2 to the power 2. I just prescribe some rapidly increasing sequence and say give me analytic function. Such an analytic function does not exist. The Cauchy's estimate puts a certain constraint on the rate at which the derivatives can grow. The derivatives can grow at most like a factorial times a power, k factorial times c to the power k for some constant c. This is the growth rate that is allowed. A growth rate of factorial squared is not allowed. A growth rate of 2 to the power n squared is not allowed. You cannot have something like 2 to the power k squared as the growth of the kth derivative. This is an extremely important point for those who are doing PDEs. This is a very important fact. All right. So now let us look at one consequence of the Cauchy's estimate. What is Cauchy's estimate? Once again, let me recall for you, is that the kth derivative of f at a modulus is less than a factorial times the r to the power k, where r is the radius of the disk over which you are computing the supremum. All right. So now let us see a consequence of this. Let us prove Liouville's theorem. What is Liouville's theorem? A bounded entire function is a constant. We have seen several important consequences of Liouville's theorem. What is a very important consequence of Liouville's theorem? in the previous lectures we have seen that the fundamental theorem of algebra falls out of Liouville's theorem, right. Liouville's theorem is the first in the sequence of in a list of theorems on entire functions. The Little Picard's theorem is a significant improvement over the Liouville's theorem. The Little Picard's theorem says that an entire function can only omit one point. Liouville's theorem says that an entire function is bounded in modulus is a constant. If it is bounded in the modulus, that means that its values are all constrained in a disk, right. So what the Liouville's theorem is that if its hypothesis says that if the values of the function are all constrained in a disk, then the function is a constant, entire functions, we are talking only about entire functions. And the Little Picard's theorem says that if the function values, if the range misses two complex numbers, then finished, the function is a constant. So you see that the Liouville's theorem is the simplest of a hierarchy of theorems on entire functions, one of the most basic and one of the most fundamental theorems in the theory of entire functions. A bounded entire function is constant. So start with an entire function f, assume it's bounded, say its supremum is m. We have to arrive at a contradiction. Alright, it's an entire function, it's defined on the whole complex number. So I am going to take a disk of radius r centered at the origin and going to apply the Cauchy's estimate. Cauchy's estimate says that it grows like a factorial times r to the power m, but this m is a constant which is independent of r, correct. Moment I have this, I can allow the r to go to infinity and then this thing will go to 0 for each k, for k equal to 1, 2, 3. For each one of these, I am going to allow the r to go to infinity and I will conclude that this thing is 0 for k equal to 1, 2, 3, etc. Correct? Is that right? Is it clear? So the derivatives, so all the derivatives at the origin vanish. So what is the power series for the function f? Constant term a naught, that's all, because all the other terms become 0. So the power series expansion is valid on what domain? It's an entire function, remember. So the power series is valid on the whole plane. The largest disk that can be inscribed in the domain is the whole plane, alright. That's Liouville's theorem. Beautiful result, and the proof is absolutely remarkable, that it's a consequence of the Cauchy's estimate, right. It's a consequence of Cauchy's estimate. So now a very important consequence of the Liouville's theorem is the fundamental theorem of algebra. What is the fundamental theorem of algebra? A non-constant polynomial has a complex root. Now I have already done the proof of this in chapter 3. We have gone through the proof of this in chapter 3. Can you recall the proof? Suppose you take the polynomial, suppose you take a polynomial pz. It's a non-constant polynomial, right? So I can assume that the polynomial is z to the power n plus something times z to the power n minus 1 plus something times z to the power n minus 2 plus leading coefficient can be 1, no, because I want to solve pz equal to 0. So I can divide by the leading coefficient and make the leading coefficient 1, is that right? So I might as well assume that the polynomial is z to the power n plus a1 z to the power n minus 1 plus etc. What is the next step that is involved? I remove the z to the power n out. So I write it as z to the power n into 1 plus a1 by z plus a2 by z squared, etc. Now what is going to happen? If z is very large, then the a1 by z, a2 by z squared, etc. are pretty small, right? And there are only finitely many of them. It's a polynomial, there are only finitely many terms, right? And I'm going to assume that z is so large that mod z will be, will be less than mod z squared. Mod z squared will be less than mod z cube. So take z to be bigger than 2 in absolute value. Mod z is bigger than or equal to 2. Fine, just to begin with. So a2 by z squared in absolute value will be less than mod a2 by z, mod z. Correct? Because mod z squared is going to be larger than mod z, no? So 1 over mod z squared is even going to be smaller. So look at what you have. Imagine what I'm deliberately not telling you the slide. I want you to imagine. I don't want you to read the slide. You take the mod pz. Mod pz will be, what was it first? Z to the power n was pulled out, right? So mod z to the power n into mod of 1 minus a1 by z minus a2 by z squared, etc. Apply the triangle inequality. Greater than or equal to mod z to the power n into mod z to the power n into 1 minus mod a1 by mod z minus mod a2 by mod z squared minus mod a3 by mod z cube, etc. But then in the denominators you have mod z squared, mod z cube. Those things can be replaced by mod z because the z is large. So what do I get? Mod pz is greater than or equal to mod z to the power n into big bracket 1 minus, I can combine everything, mod a1 plus mod a2 plus mod a3 plus mod an divided by mod z, that's all. That whole thing is a constant, no? Call that constant c. So mod pz is greater than or equal to mod z to the power n into 1 minus c by z. So if mod z is bigger than 2c, then that second factor 1 minus c by mod z is bigger than half. Correct? So what do you get ultimately? What is the conclusion of this whole discussion? Mod pz is bigger than or equal to 1/2 of mod z to the power n. This is what I meant when I said that z to the power n term is going to dominate the rest of the terms for large values of z. This is the whole what I really meant. So mod pz is bigger than or equal to 1/2 of mod z to the power n. So 1 over mod pz is going to be less than or equal to 2 upon mod z to the power n, which is less than or equal to 2 because mod z is bigger than 1. So 1 over mod pz is bounded outside a certain disk. But inside the closed disk, if the pz has no zeros, then 1 over pz is a continuous function. And so a continuous function is going to be bounded on a closed bounded disk. So inside the closed bounded disk, you have one particular bound. Outside this bounded disk, you have another bound. So 1 over pz will be a bounded entire function if pz has no zeros. Contradiction. Is the proof clear? Let's go through it. So let pz be a non-constant polynomial. Suppose pz is not equal to 0 for any z, then let f of z equal to 1 over pz. This is an entire function because this is not 0. Denominator is not 0 and pz is an entire function, and so 1 over pz is an entire function. So let us call pz as z to the power n plus a1 z to the power n minus 1 plus etc. plus an. Calculate the mod. Mod pz is mod z, straight away apply the triangle inequality, mod z to the power n minus mod an mod z to the power n minus 1 minus etc. all minuses mod an. Pull the mod z to the power n out, you get 1 minus mod a1 by mod z minus mod A2 by mod Z squared minus etc. mod AN by mod Z to the power n. Is this point clear to everybody? This is exactly what we did discussed. Now it's all there on the slide, alright. So now what am I going to do? What is the next step? Mod Z is going to be assumed to be larger than or equal to 1. So I can replace mod Z squared by mod Z etc. and I'll still get greater than or equal to, alright. So for mod Z bigger than or equal to 1, mod Z squared is bigger than or equal to Z. So A2 by mod Z squared is going to be less than or equal to mod A2 by mod Z etc. So you will get mod PZ greater than or equal to mod Z to the power n big bracket 1 minus mod A1 by mod Z minus mod A2 by mod Z minus etc. mod AN by mod Z. All these things have been combined and put down as some constant C, some constant C. And so I can assume that this is going to be bigger than half when mod Z is bigger than 2C. So outside this, so I'll take the maximum of 1 and 2C. So outside the disk of radius 1 plus 2C for example, you are going to have mod PZ bigger than or equal to half mod Z to the power n. So this is the crucial thing. This is the crucial step in the proof. Alright, is it clear? This estimate? This is the important estimate. Once you get this estimate, then you are through, practically through. Then your mod Fz is 1 over mod Pz, which is less than 2 by mod Z to the power n, which in turn is less than 2 because mod Z is bigger than or equal to 1. So you just take a reciprocal of this. Take 1 over, take the reciprocal. The inequality will reverse directions. That's what has happened. So on the closed disk, mod Z less than or equal to max of 1 plus 1 comma 2C, f of mod Fz is bounded anyway by continuity. So Fz is a bounded entire function and so is a constant. So its reciprocal is also a constant and the polynomial is constant, which is a contradiction. So Liouville's theorem is a simple consequence of the fundamental theorem of algebra is a simple consequence of the Liouville's theorem, and the Liouville's theorem is a simple consequence of Cauchy's estimate. Correct? Is it clear? It's an important theorem. We are proving very important theorems. The fundamental theorem of algebra. For the first time, perhaps you are seeing the proof of the fundamental theorem of algebra, right? Now, the next theorem that we are going to look at is the zeros of analytic functions. Now, when you have an analytic function, they have some nice properties. The zeros cannot cluster. Suppose I tell you that an analytic function, suppose I tell you that Fz is analytic. Let us assume that it's analytic everywhere, just for simplicity. Take function which is analytic everywhere. And I am giving you the following information. F of 1 is 0, f of half is 0, f of 1/3 is 0, f of 1/4 is 0, etc. Then what is the conclusion? What do you conclude from there? F of 0 is 0 because of continuity. The function vanishes at 1/2, 1/3, etc. And so by continuity it should vanish at 0, correct? Now, without doing any complex analysis, just your basic calculus will tell you what. What am I telling you? I am telling you that function vanishes at 1/2, 1/3, 1/4, etc. By continuity, you are concluding that the function vanishes at origin. What about the derivatives? I am telling you now that the function is differentiable and the derivative is also continuous. That added information I am giving you. Then can you apply the mean value theorem? Between 1/2, the Rolle's theorem will tell you that the derivative should vanish. Between half and 1/3, the derivative should vanish. Between 1/3 and 1/4, the derivative should vanish, right? Now you have a sequence of points converging to the origin at which the derivative vanishes. Therefore, what can you say about f prime of 0? 0 again. F prime of 0 is 0. Now if I tell you that f is twice continuously differentiable, then I can apply the Rolle's theorem again, right. Between 2 points where the first derivative vanishes, the second derivative must vanish. So again you will get that the second derivative is 0 and so on. So all the derivatives must be 0. And now if I tell you that the function is analytic, then it has a power series expansion and only the constant term will survive, and that constant term will also be 0 because f of 0 is 0. So this is a 0 function. Is this argument clear? That if you have an analytic function, a function is analytic in a neighborhood of the origin, and if it vanishes at 1/2, 1/3, 1/4, etc., then it must be the 0 function. Here I illustrated to you a proof using the mean value theorem, alright, because my zeros were nicely located on the real axis, but then the zeros need not be located in the real axis, it may be located all over the place. You need to slightly modify the argument, but instead of modifying this argument and trying something out, let us just try straight away go for the standard argument and let us prove the theorem. The zeros of suppose f from omega to c is analytic, where omega is an open connected domain, and I am giving you the information that f of zn equal to 0 for a sequence zn of distinct points with limit point in omega. Remember I said in the earlier example, the sequence of points is 1/2, 1/3, 1/4. It is a sequence of distinct points converging to the origin. What you need to have is that you need a limit point. Moment you have a sequence of distinct points with a limit point, then I can take the sequence I can take a subsequence converging to that. So I might as well say that Zn converges to P. Zn is a sequence of distinct points converging to P. That's also I could say that there is no loss of generality. You could assume, if you wish, that the sequence Zn's converges to P and the function vanishes at each of these points Zn, and the limit, important thing, the limit P is in the domain, important, then the function is a 0 function. Then the function is the 0 function. How do you prove this? The first step is the same as in the example. Zn's without loss of generality, I may assume that the sequence converges to P, and P is in the sequence is a sequence of distinct points. So I might assume that none of the Zn's are P. These two I can always assume. And now the f is vanishing at each of the Zn's. So by continuity, f of P is 0. By continuity, f of P is 0. So what will happen to the power series expansion for the function? The constant term will be 0. Power series at P, f of P is 0. So what is the next term? A1 times Z minus P plus etc. So Z minus P will come out and I will get A1 plus A2 into Z minus P plus A3 into Z minus P the whole square, etc. That is a power series, and let us call it sum Gz. Let us call the sum Gz, right, and repeat the argument. So you are having a power series Fz equal to f of P plus A1 times Z minus P plus A2 times Z minus P the whole square plus etc. This first term is 0, f of P is 0. F of P is 0. So it is gone. So you got f Z minus P into A1 plus A2 into Z minus P, correct? Z minus P, etc. Call this bracket as Gz. Call this stuff inside the bracket as Gz. So what do you have? F of Z equal to Z minus P times Gz. Put Z equal to Zn. Put Z equal to Zn. What will you get? 0 equal to Zn minus P times G of Zn. You get f of Zn equal to Zn minus P times g of Zn, but f of Zn is 0, right. And the other assumption is that Zn is not equal to p. So, Zn minus p is not 0. So, g of Zn is 0, and you have a sequence of points gn's are converging to, sorry, Zn's are converging to p, g of Zn is 0, g is also analytic, it is a sum of a power series. So, g of p is also 0. That means that f prime of p is also 0, correct. Continuing in this way, you will get f p is 0, f prime p is 0, f double prime p is 0. The power series representation for f, what happens to it? What happens to the power series representation for f? It is simply the 0 series. So, f is 0, the power series is going to be valid in a, remember the power series is valid where? In the largest disk that can be inscribed in omega. On that disk, we have concluded that the function f is 0. We have a domain, what is that? Let us go back to the theorem. What the theorem says? Omega is a connected open set, f is analytic, function is, and it is 0 on a sequence of points Zn, and this sequence of points converge to a point P in the domain. And then with this point P as a center, you are looking at the power series representation. Where is this power series going to be valid? On the largest possible disk centered at P that will be contained in the domain omega. On this disk, we have proved that the function is 0. What is the next thing to do? Now, I have a domain. The domain could be like a rectangle, for example, rectangle of length 5 and width 1, and the point P may be the center point. What is the largest disk? The largest disk is that disk of radius half. On that disk, we have showed that the function is 0. How do I know that it is 0 away from it? We have to work ourselves out from that disk and prove that it is 0 everywhere else. How do I do that? Somebody has used the phrase analytic continuation, that is essentially correct, but then anyway, first let me put down the problem. Now recall that the power series is valid on the largest disk centered at P that can be inscribed in omega. From this, we must conclude f equal to 0 on the whole of omega. There are two ways of doing this. Either one directly uses a connectedness argument from topology. Unfortunately, I am not going to assume that you know what is the connectedness standard connectedness argument from general topology. That is not to be expected in this course. And secondly, you cannot give that argument to your students because they are not going to understand the connectedness argument. What you have to do is you have to give an argument which is more plausible, which will be more convincing. Remember that I am not giving the full proof, we are only giving a sketch. The first part of the proof was very precise. The second part is going to use topological ideas, so I cannot make it precise. I can only give you a sketch. You have to fill in the details. To fill in the details, you have to call upon ideas from topology. One such idea is the connectedness argument, but that is not going to be satisfying. Instead, we use an argument which is much more plausible, but that is also a topological argument, by the way. It is not a connectedness argument, it is a compactness argument. Never mind. Take a point P here and take a point Q here. What are we supposed to show? We are supposed to show that the function vanishes at Q, any Q. What have we showed? We have showed that the function is vanishing at this disk, dotted disk, centered at P. What is our hypothesis? Domain omega is connected. What is the definition of connected? That means that I can join the P and the Q by a path. So I had drawn the path here, gamma joining P and Q. So in the starting point, there is a dotted disk inside which the function is identically 0. Now I am going to, now you will have to convince yourself intuitively perhaps, or perhaps it's not intuitive, whatever it is. I can, if I take a path sitting inside some open set, then I can find finitely many points in the path such that if I take a point here and draw the largest possible disk that can be inscribed. So the disks that I am going to be talking about will be the largest possible disks that can be inscribed in the domain, right. So with all these intermediate points, I am going to draw these disks, correct. And I want you to think about this, and I want you to convince yourselves, or maybe decide for yourself whether it is plausible or not, that I can plot finitely many points on the path such that, let us call these finitely many points Z0, Z1, Z2, Z3, Zm. Z0 is P and Zm is Q. And with each of these points as centers, I draw the largest possible disk that can be inscribed in the domain. What I want you to see is the disk with center P will contain the point Z1. The disk with center at Z1 will contain the point Z2. The disk with center Z2 will contain the point Z3, and so it goes. That is really a compactness argument. That also cannot be given to you precisely because it's a compactness argument. But perhaps intuitively it is more plausible than the connectedness argument.